Okay, welcome to Tuesday, November 10th. And our goal is to prepare to solve more equations that involve radicals, square roots, cube roots, and so forth. So what we're working on is radical expressions and simplifying radical expressions in a uniform way. Adding and subtracting them, multiplying and dividing them, and performing what we call simplified radical form or simplest radical form. The idea that if two people are given the same radical form, we want to arrive at one answer. We want to have rules for expressing radicals in a uniform way. And that's simplest radical form, which basic is basic English explanation. Leave no perfect powers behind. Leave no perfect powers under a radical. Leave no radicals in denominators. And third, always combine like terms. Those are the basic principles for simplifying radicals. And we'll illustrate them in several places today. Okay. Let me show you where we are on the website. Okay. I've had several cases of lagging video today, so I'll do what I can to minimize that. But if you're receiving bad video from me, it may not be a problem on your end. It may be a problem on my end. So we'll just hit the manage. The recording should come out reliably. So let's look at our website just to give you an idea of where we are today. So we're looking this week at sections 7.4, 7.5, 7.6, and 7.7. And today let's talk about addition and subtraction of radical expressions, multiplication and division of radical expressions. And then we'll get into the purpose that we've set for dealing with radicals. We would like to solve more equations. We'd like to solve equations with radicals, and we'd like to solve equations with powers. And that's going to require us literally to invent some new numbers. And that's also a topic for Thursday, the complex numbers. You're working on some homework. Tomorrow, you're handing in written homework number 8. Then we'll turn on written homework number 9. And you're working on these homeworks in the XYZ. Remember I gave you last week these radical function handouts, things to do with radicals, and you'll see the radical equations, simplifying radical expressions, and complex numbers. That'll be things that we cover this week. These handouts might be useful. I just want to look at the simplifying radical expressions handout, make sure it's what I intended it to be. So these are the basic rules for simplifying radical expressions. You can write powers or roots in either order. You have something called the product rule that A radical of a product is the product of the radicals. Quotient rule, a radical of a quotient is the quotient of the radicals. You're allowed to split radicals up by multiplication or division, never by addition or subtraction. You need to follow this special rule that unless you know a variable is not negative, when you take the nth root of the nth power, you have to protect that value with an absolute value sign. For example, the square root of x squared has to be the absolute value of x, unless you're told that x was not a negative number. But the square root of x to the fourth can be written as simply as possible as x squared, because squaring the absolute value will not be different than squaring the x. So the squaring makes that number positive. Here's some examples for combining radicals or otherwise simplifying radicals. Simplest radical form, for example, if I multiply, I'm looking at this image right here. Square root of 3 times the square root of 6 is the square root of 18. Now, 18 is not a perfect square, but there are perfect squares inside 18 of 9. And then I can split the 18 up as to 9 times 2. Square root of 9 I know is 3. Square root of 2 I don't know. So that means the square root of 3 times the square root of 6 is the same as 3 times the square root of 2 if I write it in simplest radical form. This works for any powers. The cube root of 4 times the cube root of 6 is the cube root of 24. And 24 is not a perfect cube, but it has a perfect cube inside it. So we're always looking to remove perfect powers from radicals whenever possible. I can do the same thing with variables as I can do with numbers. So sometimes it's easier to deal with variables because they don't become obnoxiously large numbers. Here's an example where I simplified a long expression that involves variables x and y and 16. Inside the 16, there's a perfect cube called 8. And I can pull that cube root of 8 out to become a 2. I've got perfect cubes of x and y. I've got x cubed with 1 x left over and 2 copies of y cubed. So I can pull out 1 x and 2 y's. I'm going to illustrate this with the problems we do today, but I'm just saying this handout is a good summary of multiplying and simplifying radical expressions. Let me stop sharing that and move over to here. So let's look at some problems in 7.4 and 7.5. And the reason we're doing this, we're not solving equations right now, but we're getting ready to solve equations that'll have radicals in them. So let's just do a bunch of examples here in these two sections. So if I had, why not start with the very beginning? So all the problems in this section, he's first asking you to add and subtract these expressions. So if I said to someone, simplify 3 times the square root of 5 plus 4 times the square root of 5, it'd be literally like saying I have 3 apples plus 4 apples. I've got 7 apples. I got 7 of these things called the square root of 5. Now you don't have to do any fancy factoring. I mean, if you want to see it factored, you can say, oh, let's factor out a root 5. And that leaves behind 3 plus 4. And 3 plus 4 is 7. But you don't have to write this intermediate step here. You can just say, I am combining like terms. And when I combine like terms, I have 7 of those things. 7 of what things? 7 of the square root of 5. Okay. So first example, if I have number 7 here, same instructions, 8 times the cube root of 6 minus 2 times the cube root of 6 plus 3 times the cube root of 6. All I'm asking you to do is total the things that I have here. 8 of these minus 2 of these, that would be 6 of them. And 6 of them plus 3 of them would be 9 of them. So I have 9 times the cube root of 6. I'm not doing anything but combining like terms.
Hey, Professor, I have a question.
Go ahead.
Does it matter in what order that we add or subtract these? Like, could we do -2 plus 3 would be 1, then 1 plus 8?
Yes, absolutely. You're allowed to add and subtract in any order. In the same way, and don't think of it as different, in the same way that if I said to you 8x minus 2x plus 3x, you could use either order to say 9x. Or think about it like this. If I said 8/3 minus 2/3 plus 3/3, well, then you're allowed to say 9/3. 9/3 is 3. But think of the thirds or the x or the cube root of 6 as an animal. I've got 8 of these animals, took away 2 of those animals, added 3 more of those animals. What do I got total? I got 9 of those animals. And it doesn't matter whether the animals are called cube root of 6 or x or thirds, as long as they're all the same animals. You can do it in any order, just like you can literally add numbers in any order. I mean, it's kind of funny when you think of this, but here are 4 problems side by side, but they're the same problem, just a different name of the things you were adding. Okay, so that's a good question. You're allowed to add things in different orders. You're allowed to add and subtract in any order you like. Okay, let's try. You know, the only thing that would get you into trouble, and sometimes people have done this, and I think you guys have asked this once of me earlier. Don't say, oh, 2 plus 3 is 5, 8 minus 5 is 3. This does not say 2 plus 3. It says minus 2 plus 3. And I think you guys even asked me that a week or two ago in a different context. So always signs belong to numbers. Don't disrespect the signs. Let me try this. 7.4 and number 13. What happens if everybody is not the same? Let's say you had 6 root x minus 5 root y minus 4 root x minus 7 root y. Now, you can't force people to be the same if they're not. You can't force apples and oranges to be the same. So here I have 4 things to add and subtract. Okay, mostly subtracting, but they all 4 don't belong together. What do I have to do? Put together the ones that belong together. I have 6 of these root x's, and I'm going to take away 4 of the root x's. That means I have 2 root x's. And then I have -5 of these root y's and -7 of these root y's. And when I total them, I get -12 root y. And you don't have to be going any further than that. In fact, you shouldn't go further than that. You can't combine these into -10 something because these things aren't the same. They're physically different. In the same way that if I said to you, 6x minus 5y minus 4x minus 7y, you'd never combine all four of those. You'd combine the x pieces, and you'd combine the y pieces, but you wouldn't combine 2x minus 12y and create -10xy's or something like that, right? Only combine like terms. Okay. But again, it doesn't matter what I call the animals. I've got 6 of these animals and I took away 4 of the animals. That means I have 2 of those animals. -5 of the animals, -7 of the animals. I've got -12 of those animals. Okay, so think about like this right here. I'm not doing anything creative yet. I'm just saying I'm adding the things that match in self-defense. I'm not doing any creative stuff. I'm just putting together the things that match. Now let's try a harder one. Because you have to look out for this. Sometimes things do match, even though they don't look like they match. So let's add these 3 things here. Add and subtract. This is problem number 17. And your first reaction is to say, well, these are 3 different people. I can't do anything about these. None of them are the same. Oh yeah, except you haven't simplified them yet. Now 20 is not a perfect square, but I know a perfect square inside 20. And so according to the rules of radicals, I can write the square root of 4 times the square root of 5, and that's 2 root 5. So I'm simplifying that radical. But then I look at these and I see the same thing, like 45 is not a perfect square, but I know a perfect square inside 45. 9 times 5. Okay, let's see if 80 wants to play ball here. Say, is there any perfect squares inside of 80? Sometimes you have to take things over here to the side and work it out. 2 times 40, 2 times 20, 2 times 10, 2 times 5. When you break 80 down all the way, what do you got? 2 to the 4th power times 5. Don't say 2 to the 4th power. That's not a perfect square. No, it is a perfect square. It's 4 squared. It's 16 times 5. So 80 is also got a perfect square inside in it called 16. And I can simplify this by saying the square root of 16 is 4. And the square root of 5, I just have to happily drag along. I don't know what the square root of 5 is. Now, I wrote too many steps here. I was being really careful with all the steps. But do you see what happened? These three people looked totally different, but they're not. They were all actually made out of the square root of 5. And now this looks like one of the problems we did earlier. I got 2 of them, and I subtract 4 of them, and then I add 3 of them. When the dust settles, I just have the square root of 5. Just one square root of 5. Look at that. So that came dramatically easier. That came dramatically easier after I combined like terms. So combining like terms is like an overriding command. Even when things may not look alike. Now, again, calculator doesn't tell me what's true or false, but I'm just kind of curious that that simplified so nicely. So I just want to see the comparison side by side. I'm going to struggle getting my calculator under the camera here nicely. So if I take the square root of 20 minus the square root of 80 plus the square root of 45. This is what I get. And if I compare that to the square root of 5, I'm hoping it's exactly the same. So it is. Now remember, nothing's true because the calculator tells me so, but I just want to put that into your mind. They did not look alike at all, but not only were they like terms, but they got dramatically simpler when I cleaned it up using the like terms. And this is the reason why we're doing it. We want everybody to write our answers in the same way. And I want to compare my answer to your answer or her answer to his answer. So if you write root 20 minus root 80 plus root 45, and she writes root 5, well, you know what? You're both right, except it's very hard to tell if you got the same answer. So this is what I have. I had these rules called simplest radical form. Pull out all perfect squares that you can find, and then combine like terms until you and I, or you and she, any 2 people can say, oh yes, we do have the same answer. Don't worry, we have the same answer. Okay, that's the purpose of doing this. Let me set my calculator aside. Some people got fancy calculator program inside their computer, like a TI program that's on their computer, and I don't have that. At least I haven't been able to find one that I like or trust. So I'll just stick to bringing my calculator in. Look at 21. That is the entire game today. Let's take things that don't look alike. Let's take things that look different and see how small we can make them. See how compact we can make them. So in 21, I've got 5x times the square root of 8 plus 3 times the square root of 32x squared and the last piece is minus 5 times the square root of 50x squared. Now, I've got this situation where I'm going to be taking the square root of x squared, right? And I've got to be nervous about that. Is the square root of x squared equal to the absolute value of x? In general, yes. But look at the instructions of this problem. The problem said, assume all the variables are non-negative. The whole batch of problems. They said, assume all variables are non-negative. That's just a fancy way of saying not negative. So I don't have to write the square root of x equals x squared. Instead, I'm allowed to go simpler and just say square root of x squared is x. Okay, where am I going to use it? I'm going to use that on this x squared here and this x squared here. But can I do even better with the numbers, right? Can I do better with the numbers? What about 8 itself? There's a perfect square inside 8. So get ready to yank it out. What about in this second radical? There's 2 perfect squares. X squared is a perfect square, certainly, but so is inside 32, 16. So I'm going to pull out the square root of 16, call it 4. I'm going to pull out the square root of x squared, call it x. Same thing here. Got a perfect square, square root of x squared, no doubt. But inside 50, there's a perfect square called 25. So you've got to like know and recognize perfect squares, perfect cubes, all kinds of stuff like that. So let's not be in a hurry. Let's just multiply things out very slowly. I'm allowed to separate these two, and the square root of 4 is 2. And the square root of 2 I can't touch. At least I don't know how to write it simpler. So this is 10x root 2. That's this first piece. Let's look at the second piece. 3 times the square root of 16 times the square root of 2 times the square root of x squared. So that's 3 times 4 times the square root of 2 times x. Now, you can write these people in order. Most people will write everything that's outside a root in front, and then everything that is the root next. So people generally write this as 12x, the things outside the root, times the square root of 2. And then lastly here, I have minus 5 times the square root of 25 times the square root of 2 times the square root of x squared. Minus 5 times 5 times the square root of 2 times x. I'm allowed to say the square root of x squared is x because I was assuming the variables were not negative. When I put all those people together, minus 25 x's times the square root of 2. Now I do have 3 common terms. I have 10 of these x root 2's, 12 of the x root 2's, and then I'm going to take away 25 of the x root 2's. So in this problem, there's only one animal, and it's called x root 2. And the question is, how many do you have? Sorry, somewhere I got interrupted there by a phone call. And I would have said that I turned the phone call off. So hang on. I got to go through my computer and find out where the phone call is. Okay. That's
Hi.
hello?
Hello, is this Dave?
This is David, but right now I'm teaching a class. Can I call you back later?
Okay. Sure. You have a great day, sir. Bye-bye.
Bye. Okay, that was weird. I don't know who that was. But nowadays, not only do they got your cell phone number, then they got your Google Voice number. So you cannot have peace and quiet anywhere. Okay, back to work. These 3 things originally looked very different. And it turns out, though, that they were all the same. I have 10 of them, and then I added 12 of them, and then I took away 25 of them. 22 minus 25 is -3 of them. Okay. That's all you're doing today, is taking pieces and combining them and organizing them as far as you can. And the purpose is that so you and I can compare answers quickly and easily. Let's try some other one. Okay, good.
So if, like, let's say, like, there was the square root of 5 and then the cube root of 5, would those be able to be combined or no?
Good. That there are problems like that coming our way. I'll show you. Now the problem is the answer is yes, they can be combined, but not necessarily in an inexpensive way you might wish. Let's look at this. But that's a great question. I mean, because your brain is telling you that I should be able to combine these somehow. And the answer is these can be combined, but maybe not in the way you expect. See, we have to use those rational exponents. Think of the square root as 1/2 power. And think of the cube root as a 1/3 power. Now I've got the same base here, but I can't just like add those 2 expressions and pretend that I apply the power to the 5 or different versions of that power to the 5. I could try to compare these people by making these fractions have common denominator. Let's try it. Instead of 1/2, I could say 3/6 here. Instead of 1/3, I could say 2/6. then what could I do next with this? Well, again, I've got this 5 that looks alike between the two. It's almost like I could say, well, here's 5 to the 3, 6 plus 5 to the 2, 6 is like saying, let's factor out a 2/6 power of 5. And that would leave behind 1/6 power of 5 plus 1. Right? When you multiply things with a common base, you add the exponent. So 2/6 plus 1/6 is 3/6. And 5 to the 2/6 times 1 is 5 to the 2/6. Now let's write that is 5 to the 1/3 and 5 to the 1/6 plus 1. I mean, I've combined them, but I don't think I've combined them in a useful way. Let's go back to roots. This is the cube root of 5. This is the 6th root of 5 plus 1. So, the burning question is, are you joking? Are these really the same? Let's type it in and find out.
But since 5 to the 3, 6 and 5 to the 2, 6 have the same bases, wouldn't you just be able to add them as 5 to the 5, 6?
No, okay, so that's the next, okay, so you're anticipating the next example I'm doing. I cannot
Sorry about
add across powers, and I'll show you that in a second. So first, let's decide if this is true. And this doesn't look useful at all, but it is just a question of, is it true or false? Let's find out if it's true or false. So square root of 5, and then I'll explain why you can't do what you just said, plus math cube root of 5. Okay, so the square root of 5 plus the cube root of 5. Let me get back my little calculator stand, which is just a couple Rubik's cubes. Square root of 5 plus the cube root of 5 is 3.94 and change. Now, what was I going to compare it to? The cube root of 5 times the cube root, or the 6th root of 5 plus 1. Okay, so cube root of 5 times parentheses the 6th root of 5 plus 1. It's the exact same number. Now, your problem is right now, it's very hard to believe, wait a minute, you called that simplifying? It doesn't look simplified to me. But at least they're equal. At least they're honestly equal. Now, let's think about what you were saying. If I had 4 squared plus 4 cubed, can I just write that as 4 to the 5th power? I'm a little bit nervous because 4 to the 5th power, first of all, is a huge number. 4 squared, I understand, is 16. 4 times 4 times 4 is 64. But when you check that out, and you could ask your calculator what 4 to the 5th is, calculator says 4 to the 5th is 1024. 1024. So you cannot add these things with a common base. Why? Because they have different exponents. You could factor out a 4 squared. You could say 4 squared, and that leaves behind 1 plus 4. And 4 squared is 16, and 1 plus 4 is 5. So 4 squared plus 4 cubed, as you see, is 80, because 16 times 5 is 80. But not just add the exponents. Now, you are remembering a true rule, and that's why I spend time to go through this here with you, because it's really important. You're remembering a rule, and you're mixing it up with something else. You're remembering this rule. If I have 4 squared times 4 cubed, I'm allowed to add the exponents. But you never can add exponents separated by addition or subtraction. This is 4 times 4 times 4 times 4 times 4. That is 5 fours. And if you multiply 5 fours together, you do get 1024. So let's think like this. If you have a common base, you're allowed to add the exponents, but never if you have common base added together. That's never true. The other thing people do with this sometimes, like, what's the square root of 4 times the square root of 25? Well, because I'm multiplying 2 square roots, I can call that square root of 100, which is 10. That makes sense, because the square root of 4 is 2, and the square root of 25 is 5. And 2 times 5 is 10. But I can't say the square root of 4 plus the square root of 5, 25, is the square root of 29. That doesn't make any sense. Because the square root of 4 is 2, the square root of 25 is 5. And you can't say the square root of 29 is 7. Well, that's impossible. The square root of 49 is 7. The square root of 29, I don't know what it is. It's some crazy number, but it's not 7. Okay, so when you're dealing with exponents or roots, you can combine exponents or roots when you're multiplying or dividing people. You can never combine exponents and roots when you're adding or subtracting people. Now, to finish your question, because it was a really good question, and then we'll come up on a break. So look at this problem that we just did here with the 5s. We went through this torture with the 5s. But we actually showed that that was correct. If I was multiplying root 5 times the cube root of 5, would that be easier? It'd be easier because now I'm multiplying things with the same base. 5 to the 1/2 times 5 to the 1/3. And since I'm multiplying things with the same base, I'm allowed to add the exponents. 1/2 plus 1/3. And what is that going to give me? 3/6 plus 2/6 is 5/6. So the square root of 5 times the cube root of 5 is equal to the 6th root of 5 to the 5. Now, I'd have to think about what 5 to the 5 power is. Excuse me. 5 times 5 is 25, times 5 is 125, times 5 again is 625, times 5 again is 3125. 5 to the 5th power is 3125. Well, let's find out. Is this really true what I just did? Let's find out. Okay, back to my calculator stand. Square root of 5 times the cube root of 5 is that number right there. I better check 5 to the 5th power. Is it really 3125? Okay, got that. Now what's the 6th root of 3125? I go in here and take the 6th root, 3125. That's the same number. Again, it's not the same because the calculator says it's the same, but as far as the calculator is concerned, yes, they're exactly the same number. Okay, good. That is a good question you ask, and it shows you how difficult it is when you're adding or subtracting something versus when you're multiplying something. In some sense, it's easier to multiply than it is to add or subtract. Okay. Let me try one more here. We're going to just keep doing example like this. Let's look at something like 31, just because it looks ugly. In some sense, I want to show you that doesn't, even if these things look ugly, as long as you follow these rules of simplifying, pulling out the perfect powers, and combining like terms, you're going to be okay. So I'm copying this really carefully. And sometimes the print on all these numbers and letters is so small, I gotta have my glasses on. $48, x to the 4th, y to the 5th. Yeah, so when you copy these problems, always make sure you copy them very carefully. If you get one of these numbers wrong, then it probably ruins the combinations. And again, we're allowed to assume all variables. These were in the instructions to the problem. Are non-negative. Okay, let's think about this as we go on. Now, it's first of all, it's 4th roots. So I got to talk about 4 powers, perfect 4th powers. And I do see perfect 4th powers in some places. There's a 3 and a 4th power of y and one more y left over. So there is a perfect 4th power right there. And then I'll say, oh, there's a perfect 4th power of x. oh, there's a perfect fourth power of X and a perfect fourth power of Y. So I feel good about that. Now it's these other numbers, 243 and 48. Are they perfect fourth powers? Do they got perfect fourth powers in them? Well, that's what we got to figure out. 48 is what? 2 times 24? 2 times 12? 2 times 6? 2 times 3. There is a perfect fourth power inside 48. 48 is 16 times 3, and 16 is a perfect fourth power. Okay, that's going to let me fix that one. Fourth power of 16 times 3, that'll be the 48, x to the fourth, y to the fourth, and one more y. Okay, so I see my perfect fourth powers right there. How about 243? I'm guessing there must be a perfect power inside 243. 3 to 81. Yes, 81 is a perfect fourth power. You think of 81 as a perfect square, but actually 81, sorry, slide my paper up. Actually 81 is a perfect fourth power. 81 is 9 times 9, perfect square, but it's also 3 times 3 times 3 times 3, which is 3 to the fourth. Okay, so that means I get to break this one down. Fourth root of 81 times 3 times x to the fourth times y. And there's my perfect fourth powers. Now let's remove the perfect fourth powers. The fourth root of the fourth power of y is just y. So this is 5xy times the fourth root of 3y. Think about the 3y as not being strong enough to escape. There's no 3 4s, or there's no 3 to the fourth. There's no y to the fourth. These people are left behind in this prison, in this fourth root prison, because they don't got enough juice to get out. They don't got enough powers to get out. Now the fourth root of 81 is 3. So here on this one, I can pull a 3 out. I can pull an x to the fourth. Fourth root of x to the fourth brings out an x. And I have a y already outside. But who's left behind in prison? That 3 and that y. That's interesting. Now these look alike. And I can see that these are going to look like again. Okay, prison break. Fourth root of 16 is 2. Fourth root of x to the fourth is x. Fourth root of y to the fourth is y. And who's left behind? The people that weren't strong enough to get out. That's that 3 and that y. And then all of a sudden, what? These 3 things that looked very different, you suddenly say, oh, they're not different at all. They were not different. I've got 5 of these xy fourth root 3y. Then I've got 3 of the xy fourth root 3y. And here's 2 of the xy fourth root 3y. Just say it like that. I've got 5 of these animals, 3 of these animals, 2 of these animals. I've got 10 of these animals. So that became dramatically smaller, dramatically easier than it looked at the start. So that makes us feel good that we clean this up significantly. We have to clean it up correctly too, but we clean this up significantly by removing all the perfect fourth powers. Okay, I'm going to give you some more examples of this, but this is the game. A whole day today, this is the game we're playing. I'm going to play it with multiplying and dividing when we come back. So let's just check this out. Let's come back. And I'm talking about 5 minutes. So stretch your legs for a few minutes. And we'll come back and try some more. Okay, I'm going to mute my microphone while I get up and stretch my legs. Okay, we're back here. I had to sneak a little lunch in there, sorry. Yeah, so sometimes it's remarkable how things, they don't seem they're the same, but they're the same. Now, I want to do one more problem here and then show you a peculiar kind of problem that he's got in this section. And it's almost like it was to warn you about combining things illegally. So first, let's just do let's do a couple problems here. Okay, bring that out. Bring that out. Three. I'm just numbering my papers so I can post them again after class. Let's look at this problem. Let's start to think about dividing almost. 7.4, number 39. So we got the square root of 18 over 6 plus the square root of 2 over 9. So first problem where we've actually had some fractions to deal with. Okay. Again, on my end, I see a lot of video lagging, so I apologize for that. And the recording should come out okay, but right now you have to be patient if your video is lagging in front of you. It may not be your fault. Okay, let's say 18 root over 6 plus 2 root over 9. Can these be combined in any way? What does the inclusion of the fractions here do to the problem? Well, I certainly see things that I can simplify. Like I know there's a perfect square inside 18 called 9. And I see a perfect square of 9 right here. So I could begin by writing this by concentrating on those perfect squares. So I'm allowed to separate this quotient into two radicals being divided. So I'm allowed, no matter what radical I'm using, to separate two things that are being multiplied into two radicals. I'm allowed, no matter what root I'm using, to separate things that are being divided into two radicals. I am never allowed to separate two things that are being added or subtracted into two radicals. Sometimes I'm even nervous about writing something like this down because all you remember when people write down stuff is what they wrote down, right? You never can split a radical across addition or subtraction. You can always split a radical across multiplication or division. Okay, so remember those rules. And now I'll take care of the perfect squares that I see. This is a square root of 2 over 3. And the square root of 9 is 3. So this says 3 times the square root of 2 over 6. Now I can simplify further. 3 divided by 6 is 1 divided by 2. So now I have square root of 2 over 2. When I cancel 3 over 6 to be 1 over 2, plus the square root of 2 over 3. Can I combine these? Well, yes, I can, because I can make common denominators. I might as well have just kept that 3, 6 sitting there, right? Because if I choose common denominator here, it's going to be denominator 6. And I have to multiply this one top and bottom by 2 to create that 6. I have to multiply this fraction top and bottom by 3 to create that 6. So when I get done, what have I decided? I've got 5 times the square root of 2 divided by 6. These two things didn't look like they belonged together, but after I cleaned them up, they turned into something relatively small and simple. Let me show you those side by side on the calculator, just to reinforce that. Okay. I've got some serious lag happening in front of me right now. So let's do square root of 18 divided by 6 plus the square root of 2 divided by 9, and compare it to 5 square root of 2 divided by 6. 5 square root of 2 divided by 6. It's the same number. Okay, so these two did simplify nicely. Now, look also at this problem that he has in the next section, before we go on to the next section. Why would he ask you questions like this in the book? And this is not working out on the camera. So I'm going to see if I can log into our book here and show you what he wrote. Why did he ask you to compare the things that he has here? So let me log into our account. And let me pick up our book here. Looking at that, looking at that. Let's go backwards. I'm in the right course. Okay, that's better. I'm in the book. And I got to log into the book too. And then I'll gotta turn on the screen for you. So this is small to read even when the camera's working. So let me show it to you in the book. Section 7.4. Get rid of the videos. Section 7.4. Why does he ask you questions at the end like this? (45 through 48). Use a calculator to find the decimal approximation of root 2 plus root 3 and root 5. He wants to break you of the habit of saying, even accidentally, that root 2 plus root 3 is root 5. I mean, I can see why people want to say that. What about root 7 minus root 5? Isn't that just root 2? No, he wants to break you of that habit. So, just in case you were feeling that these are equal, let me get back to the paper. Just in case you were about to say that these are equal, he says, why don't you compare them? Square root of 2 plus the square root of 3. I get 3.14 that, but what's the square root of 5? Square root of 5 is definitely less than 3. 5 is less than 9. Okay, so he's just trying to give you some visual evidence. Wait a minute. Square root of 2 plus the square root of 3 is not the square root of 5. No. Square root of 2 is about 1.414 and change. Square root of 3 is about, what is the square root of 3? 1.7 something? 1.732. And the square root of 5 is about 2.236. That's what we got here on the screen. So never can you combine two roots into one root separated by a plus sign. Just never is legal. Okay. Let's look at one more problem that he wrote right there. Use a calculator to find the decimal approximation for root 8 plus root 18. Is it equal to the square root of 26 or the square root of 50? Let's try it. Square root of 8, square root of 18. I'm supposed to be adding them, sorry. Let me get my little stand underneath here. Supposed to be adding these. There. Sorry, I've got a mess going right there. Square root of 8 plus square root of 18. Now he said compare that to square root of 26 and the square root of 50. Square root of 26. That's not the same. Square root of 50. That looks like the same as the square root of 18 plus the square root of 8. So what's he saying to you? I bet if I simplified square root of 8 plus square root of 18, and if I simplified square root of 50, I better get the same thing. Even though the square root of 8 plus the square root of 18 doesn't look like the square root of 50, they must secretly be the same. So let's compare. Sorry, get back to my paper. Square root of 8 plus the square root of 18. Square root of 50. Well, now you know how to play the game. You look for perfect squares. This is 25 times 2, which is 5 root 2. This is 4 times 2, and 9 times 2. That's 3 root 2. Sorry, 2 root 2 plus 3 root 2. That's 5 root 2. So these actually are the same. Even though originally they look totally unrelated. Now, you don't always have time to go hunting through your calculator to tell whether people are the same or not. The reason I'm emphasizing the calculator a little bit today is because I want to say to you, well, if you were not sure and you could compare with a calculator, that give you a tip as to whether you were doing it right or not. Okay. This is section 7.4. Let's do the same thing now in section 7.5, but we're going to do it with some addition and subtraction included, some multiplication and division included. Let me label that. Let me slide over to section 7.5 here. And show you one additional new technique. Okay, so 7.5. What happens if we multiply or divide expressions? So what's the square root of 6 times the square root of 3? And according to our rules, we're allowed to combine two things that are being multiplied. We're allowed to combine two radicals that are being multiplied into one radical. That's the square root of 18, which is the square root of 9 times 2, which is 3 root 2. Right? So that's the theme. They don't look like this, but you can check that the square root of 6 times the square root of 3 is 3 times the square root of 2. Look at number 7. Involves the cube roots. Here's 3 times the cube root of 3. And here's 6 times the cube root of 9. How do you bring these together? Well, you have numbers outside the cube root and you have numbers inside the cube root. And since you're multiplying, you're allowed to bring the two cube roots together. You can say, I'm going to combine like terms. The things that are outside, I will multiply together. And the things that are inside the cube root, I will multiply together. So you can write one expression with one cube root. Now, previously, check this out. There's no perfect cubes inside this cube root. That's just 3 to the first power. There's no perfect cubes inside this cube root. But now when you put them together, you get a perfect cube of 27. Here's 1 3, not enough to escape. Here's 2 3s. It's a cube root, so 2 3s are not enough to get out. But when I multiply those two roots together, I have 3 3s inside. I have 18 times the cube root of 3 cubed. That's a perfect cube. And now the 3 can escape. 18 times 3 is 54. That's interesting. These two roots turned out to be, in the end, simple and rootless. You see what happened? I kind of filled up the root. I had 2 cube roots that were not full. I didn't have enough powers of 3 to escape in either case. But when I multiplied them together, it filled up the cube root. And the whole thing became an expression with no root in it. Just checking again. And the video is going to have to catch up to me, but I'll just say 3 times the cube root of 3, excuse me, times 6 times the cube root of 9. Somehow when I multiply that whole mess, I get 54. Oh, it was a little bit in the glare there, sorry. When I multiply that whole mess, I get 54. This is a really important example that we're going to use in a second. And remember that phrase. It seems like I filled up the radical. Or filled up the root. Now it was perfectly full root. And so the root went away. Let's try something else. What happens if I have a couple of people multiplied by a couple of people? Let's say I have 3 root 6 plus 4 root 2. So this is a problem of foiling or distributing. Root 6 and 2 root 2. Let's multiply this out and see if I can make it simpler. Well, this is just like A plus B times C plus D. I've just got 2 people multiplied by 2 people. I'm just going to FOIL it out like I would FOIL out anything of that nature. I mean, literally foiling. So 3 root 6 times root 6. That's the first times the first. Outside, 3 root 6 times 2 root 2. And I'll multiply like I did above. The people outside belong together. 3 times 2 is 6. The people inside the roots belong multiplied together. Root 6 times root 2 is root 12. And the inside pieces, 4 root 2 times root 6. And the last piece times the last piece is 4 root 2 times 2 root 2. I got to clean this all up right here. Now, notice you could call this root 36, but then root 36 is just 6. So right now, this is 3 times 6. Root 6 times root 6, you can just straight away call that 6. So root 6 times root 6 is the square root of 36, which is 6. Okay, here we got 3 times 2 is 6, and square root of 6 times 2 is 12. Square root of 12. Here you got 4 times the square root of 12. And here you have 4 times 2 on the outside, and the square root of 2 times the square root of 2 on the inside. That's 8 times 2. Square root of 2 times square root of 2 is 2. Now, everybody's not looking the same, but I do have some common terms. I can improve the square root of 12, though, right? 12 is 4 times 3. So both of those can be simplified. This is 6 times 2 times the square root of 3. This is 4 times 2. Square root of 4 is 2 times square root of 3. The first and the last were not going to be a pain. So that's just 16 on the back and 18 on the front. I saved those for the end because they were easy. So what do I got right here? I got root 3 twice. Here's 12 root 3s. Here's 8 root 3s. 12 plus 8 gives me 20 root 3s. 18 plus 16 in front gives me 34. So this expression, when I multiplied it out, does become smaller. And it involves the root 3, where none of these people seem to have root 3s in them. And technically, there are root 3s hiding inside the root 6s. But this expression is easier to work with than multiplying out these 4 pieces. I wish I could bring it together to a single number. But, that is a single number in its own right. It's just, it's made of these 2 different kinds of pieces. I just want to keep emphasizing this, that these are the same. So I want to say this again. 3 root 6 plus 4 root 2 times root 6 plus 2 root 2
We found the source.
is
We found the source.
excuse me, hang on. So I just want to show you that these are matching. That's 68.64 and 34 plus 20 times the square root of 3 is the same 68.64 and change. If you ever feel like you need to compare things like that, see if you have simplified it correctly. You can compare them on your calculator screen like that. Okay, good. Let me show you an entirely different game here. And this game that I'm about to show you is the last level of sophistication in simplifying radicals. So I've said to you, you simplify radicals by combining like terms. You simplify radicals by making sure there's no perfect powers left behind. But I had one more statement here at the very beginning. It's also helpful to simplify radicals by not leaving a radical behind in the denominator. And at first, that seems like a harmless thing to do. Who cares if there's a square root of 3 in the denominator? But for the purposes of comparison, if we want to compare 2 things side by side, we would like to remove radicals from denominators. It makes it easier to divide if you're dividing by a whole number. So this is the last step in simplest radical form. And it's called rationalizing the denominator. Or if you like to say it this way in English, leave no radicals inside denominators. Let me tell you why people want you to do this, and then I'll show you how to do it. Okay. Let's say that I wanted you to divide 7 by the square root of 2. Now, you may not feel that that's something you're going to do with your bare hands anyway. But if you were forced to do it with your bare hands, it would be a serious problem. Why? Because the square root of 2, as far as numbers go, never ends. So how do you divide by, like, gotta write and read at the same time? How do you divide by 1.414? 213562. And forever it keeps going. How do you do a long division when the thing you're dividing into it hasn't even stopped yet? Well, you're in deep trouble, because you could say, well, I'm going to multiply by 4. And you can multiply this by 4. But the trouble is, you'll never stop multiplying it by 4. So sure, I can multiply this by 4. I get 5.6, 5, 6, 8, 4, and 12 is 5, 2, and 4. I mean, I'm going to have to constantly carry into the next column, and I'm going to be going left forever. It's like a never-ending chore. On the other hand, if I do a very silly trick, I can move this radical from the denominator to the numerator. In the numerator, I'm not so scared of it. Let's do what we just did on that previous problem where we filled up the radical. That cube root of 3 times cube root of 9 magically became the cube root of a perfect cube. And that meant the radical went away. What if we did the same thing here? Square root of 2 is not full yet. But if I multiply by another root 2, then it is full. It's the square root of 4. And the square root of 4 is easy to deal with. Now, you can't just multiply the bottom by the square root of 2 and ignore the top. So I have to multiply the top by the square root of 2 also. So what I've just shown you is that 7 divided by the square root of 2 is the same as 7 times the square root of 2 divided by 2. This game where you got the radical out of the denominator, this game is called rationalizing the denominator.
But how would that make it any easier to divide if you still have to deal with the radical on top?
Good, good, perfect. It's like I planted you. Well, let's write here what 7 root 2 is. It's 989, 949. I'll write it all down off screen here. 494, 937, and that goes on forever. But do you see? You still say, I'm still screwed. There's a never-ending number there. Ah, but the never-ending number is inside the radical. And what difference does that make for dividing? It makes dividing simple. Okay, how many times does 4 go into 9? I'm sorry, how many times does 2 go into 9? Excuse me. It goes in 4 times. And then I have 1.899494937. Okay, how many times does 2 go into 1.8? Goes in 0.9 times. And there's 1.8, and that leaves 0.099. In other words, I can put 2 into this number all day long because I just have to do it 1 digit at a time. And when I get tired, I can stop after 10 or 20 digits. But here, I never even got past the 4. Now, what I'm saying is, in a sense, a little bit artificial, because if I tell you to divide this, and if I tell you to divide this, neither one of us, not you or me, is going to write down long division. In fact, practically the only way we would know how to do this easily is with a calculator. But the habit from when people used to program computers to do this, when people first set up tables for doing this, the habit of having the square root to the bottom was so annoying. They said, let's write a rule that no one is allowed to leave square roots in denominators. So actually, people call this simplified, even though it looks larger than that. People call this not simplified. And today, when you and I have a calculator, we just say, what's the big deal? They're the same number. Try it out. 7 divided by the square root of 2. 7 times the square root of 2 divided by 2. Just in the age of the calculator, we say, you know, who cares which way I write it? I get the same number. It turns out that there's still reasons that your life is easier when your denominators don't have radicals in them. So he wants to train you to write things without radicals in the denominator. Let me give you another example. This is problem like 60. What happens if I have 5 divided by the cube root of 3? Now there's a radical in the denominator, and 3 is not a perfect cube, so I cannot extract anything there. But I can fill up the radical. How do I fill up the radical? I've only got 1 3 in there. How many 3's do I need to put in there so that they escape? I need to put 2 more 3's in there so that they escape. Okay, let's multiply the bottom by the cube root of 9. Just like that previous problem. Of course, if I multiply the bottom by the cube root of 9, I have to multiply the top by the cube root of 9, or else it's not legal. It's not fair. So the top becomes uglier, but the bottom becomes sweeter. The bottom is a perfect cube. So apparently, 5 divided by the cube root of 3 is the same as 5 times the cube root of 9 divided by 3. And this bugs the heck out of people the first time they see it, because we call this side simplified because there's no radical on the bottom. And we call this side not simplified only because there's a radical on the bottom. What are you talking about? The left side is clearly simpler. No, just because it has less pieces, that doesn't mean it's simpler. We call this simpler because there's no radical in the denominator. So when someone says to you, rationalize the denominator, all they're saying to you is get rid of the radical in the denominator by pumping it full of whatever you need to make it a perfect square or a perfect cube or a perfect whatever power you're dealing with. It kind of bugs you the first time you see that, like, what do you mean this is simpler? First thing you say is, what do you mean they're equal? But it's easy enough to show you they're equal. But this one we call simpler, the simplified radical form. I've rationalized the denominator. Just for fun, let's show you that 5 divided by the cube root of 3 is the same as 5 times the cube root of 9 divided by 3. It's the exact same number. But that looks more complicated. It's got more pieces in it. No, it's simpler because I've got no radical in the denominator. Okay, one more. There's another batch of problems in here looking like this. And I'm going to write it on the piece of paper. What happens if you have to simplify away a radical in the denominator, but there's more pieces down there? So you have to use your perfect square trick, difference of two squares. So, for example, in problem number 91, let me lower my paper, sorry. How can you simplify square root of 5 divided by the square root of 5 plus 1? It's not a complicated thing to begin with, but there's no perfect squares undone. There's no common terms that I haven't combined. It doesn't have very many terms. The only thing that offends me right here is that radical 5 in the denominator. That's offensive. No radicals in denominators. But I can't just multiply by root 5, top and bottom, because that'll take this and turn it into a 5, but it'll create another radical over here. Now, I need to use that famous formula. the difference of two squares. Remember, a plus b times a minus b has a special form. A squared minus b squared. You say, what does that have to do with this? Well, look what would happen if you would multiply the bottom. Pretend it says a plus b right now. What would happen if you multiplied the top and bottom by a minus b? The a is the root 5. The b is the 1. So let's multiply by root 5 minus 1. You know what that does is it kills the radical. How does it do that? Well, root 5 times root 5. Let's FOIL. Root 5 times root 5 is 5. Root 5 times minus 1 is minus root 5. Root 5 times plus 1 is plus root 5. And minus 1 times plus 1, minus 1. It looks messy until you stare at it for a second and say, oh my gosh, I killed the roots. Minus root 5 plus root 5, no more roots. And I just have 5 minus 1 is 4. Now, there's no good deed goes unpunished. You've heard that saying, right? So you cannot just multiply a bottom by root 5 minus 1 unless you multiply the top by root 5 minus 1, or else you'll screw up the fraction. So now I've got to multiply the top by root 5 minus 1. And that is distributing too. Root 5 times root 5 is 5. And root 5 times minus 1 is minus root 5. Now let's look at the beginning and the ending side by side. And say to you what? Who in their right mind would say the right side is simpler? Why do I call this simpler? Only one reason. I've got no more radicals in the bottom. You cannot say to me that right side looks better than left side, except that I've got no radical in the bottom. Are you sure these are the same? Are you sure those are the same? I'm curious. But you know I'm just playing with you because we're going to see that they're the same.
So will this same method work if there were two radicals in the denominator? Like
Yes.
square root of 5 plus square root of 4.
Right. If that would have said square root of 5 square root of 3, then you do the same trick. You multiply with square root of 5 minus the square root of 3. Because what does that trick do for you? It squared away the problem. And so you see the problems next to it like that. Now, whenever you have a square root plus or minus something, this trick is going to work. Now, just to make sure everybody's happy, say square root of 5 divided by square root of 5 plus 1. That's that number. Oh, sorry, I wanted minus, didn't I? No, I wanted plus. What am I doing? Oops, sorry. That was a plus sign originally. I just miscopied it. So that's right. Now, what did we work it out to be? 5 minus root 5 divided by 4. 5 minus root 5. So this is like backup. Say, okay, I know I'm right. And I'm not telling you that the right side is prettier, except that it's got no radical in the denominator. So whenever someone uses that word rationalize, what does it mean to rationalize? It means to make that denominator empty of radicals. Why don't they call it radicalize or unradicalize? No, it's because what you're making is you're making a rational expression where the radical is in the numerator. So whenever someone says rationalize the denominator, that's what they want. They want you to rewrite it so that there are no more radicals downstairs. Okay, it takes a little bit of practice, but those are the two tricks you use. You fill up the radical, or you use the difference of two squares. Okay, I'm going to get this all scanned and posted and video posted. You guys are working on a homework. You dig into that, and we'll move on to the next one. I just want to say another word, and I forgot to say this earlier. You know, this is week 11. We're just cruising along. You know, before you know it, semester's over. But you know the drill now, right? You got your weekly homeworks. You got your weekly XYZs. You already took a test, and the last week I'm going to give you another test, and it's going to look very similar to the first test. So plan ahead now. Plan ahead, practicing the things you need to practice. Let's get ready for that next exam, even though it's like 5 weeks from now. Keep practicing, keep making a list of the things you need to do and know. And then we'll wrap this up successfully. Okay, I'll see you guys later, and you have a good afternoon.